can employ the same user programs even if your application comprises different Simatic controllers. Any of the three languages can be used depending on the job in hand and your personal preferences. In the overall engineering context of a machine or plant, the programming languages presented here belong mostly to the fields of implementation and module test. For programming beginners, the two graphical languages ladder and function block diagram are the ideal basis to generate a program, because the logic can be described in the form of graphical elements and is therefore easy to understand visually. In ladder, the binary combination portion of an automation task is implemented by series and parallel connections of contacts, as in an electrical circuit diagram. Each such connection is terminated by a coil which represents the output to an actuator, such as a valve or a contactor. The current, or better signal flow, runs from the left to the right, as seen by the user. But the ladder can do more than just combine binary signals. It can also be used for effective and comfortable processing of digital values. Ladder offers for this purpose an extensive range of functions which allow you to handle almost any automation task. More complex functions, such as executing a comparison operation, are implemented by inserting a box that provides the required functionality within your program. Such a box can have several inputs to receive input values and provide the result to an output. In the programming language function block diagram, or FBD, boxes are also used to implement binary combinations of signal states. As in the ladder, more complex functions are implemented by special program elements which are supplied with the required variables through the inputs. To structure the program, both languages use networks which terminate one combination sequence each, and thus represent the smallest structuring unit. Both in ladder and in function block diagram, the program to be executed is presented very clearly and can be easily documented by the addition of comments. In contrast to the graphical languages ladder and FBD, the programming language statement list, or STL, expresses a control task by a sequence of instructions in list form. Each instruction contains the operation to be executed and the operator in the form of a mnemonic code. The code is designed so that the function, in our example an AND combination, can easily be derived from the acronyms used. Likewise, the operator, for example a process input or output or a memory bit, is easily interpretable. Digital operations are processed in statement list by loading digital variables, such as two integers, and combining them, for example by an arithmetical operation. The result is then transferred into the memory. The advantage of using statement list is the very compact notation of the automation task in hand, which saves user memory resources. Depending on the program structure and the application case, you can even mix all three languages within the same CPU. These three languages have a representation format that makes them easy to learn, but offer at the same time an extensive inventory of functions or commands which allow you to handle almost any typical automation task. Several function groups are distinguished depending on the task in hand. In the function group of binary functions, all combination tasks can typically be resolved with binary operands. Special commands such as edge detection help to speed up the execution. Powerful timer and counter functions allow you to solve quickly and reliably the extremely frequent timing and counting tasks. These operations are executed directly in the CPU without any additional hardware. In the group of digital functions, variables with digital values and the information sizes byte, word or double word are processed. The functions available are comparison, conversion, and powerful arithmetical functions. The data formats used range from BCD-coded numbers to fixed point and floating point numbers. The next function group is a prerequisite for a comfortable and well-structured program organization. Block calls are the most important aid for this. A block is a self-contained section of the user program, a subroutine to all intents and purposes. By calling a block, you decide which program sections you want to process at a given moment and which not. This makes program execution clearer and more time efficient. Within a block, the program flow is controlled by means of so-called jump functions, which allow you to execute or to skip certain program sections depending on the current result of logic operations. The last function group provides for powerful processing of data handling tasks. Such tasks can be, for example, the editing of formulation values or the transfer of large data volumes between different CPU storage areas. The STL language in particular offers a variety of powerful addressing and register operations. You can, for instance, use the indirect addressing options of data areas, which provide for runtime calculation of variable addresses and thus allow comfortable editing of user data. The very extensive range of functions provided by the three basic languages ladder, function block diagram, and statement list gives you the means to resolve all typical automation tasks quickly, effectively, and therefore economically. Another essential element for handling your automation tasks, in addition to the function range of the three languages as described above, is the program editor, which you use for actually developing your program. Since one and the same program editor is used for ladder, FBD, and STL, you can generate your program block by block and specify the programming language individually for each block as required. The program editor lets you choose between two types of programming. With source-oriented programming, you write a program source which is then compiled into the executable program code. With incremental programming, which we are going to present to you here, the program is immediately checked and compiled as it is entered, so that only syntactically correct blocks are created. We will show you here the main function areas of the program editor, which are displayed in different windows. Navigation in the editor is made quick and easy by the editor's Windows-conforming user interface with its familiar look and feel. Let us first have a look at the Program Elements catalog, which, like all editor windows, can be shown or hidden. The catalog contains in a clearly arranged structure all available graphical program elements for the programming languages ladder and function block diagram. It also shows you the user-created blocks and the system function blocks provided by Step 7. The elements and blocks listed here can now be quickly and comfortably placed in your program by drag and drop or by double-clicking. To generate the program, the editor offers you a so-called program generation area. You use this area to structure and develop your program. The editor assists you, for example, by creating networks, which are self-contained program sections within a block. Each network can be given a title to allow quick orientation in very long programs. Moreover, networks can contain a freely editable comment in which the program content is precisely and exhaustively described. In a detail window, you can call up additional information which you need as you develop your program. For instance, you can display in this window for a better overview all global variables used so far in a project, such as inputs, outputs, timers, or counters. A very useful feature during program generation is the context-sensitive help function. When you highlight an object and hit the F1 key, a help window is opened with additional information on that particular object. No more laborious searches through lengthy user manuals are necessary. To make programming even easier, the program editor offers you the possibility to assign symbolic addresses to the operands and variables used in the program. Symbolic addressing uses names instead of the numerical absolute address. This makes your program more easily readable. With the program editor, you can edit the symbolic addresses of both block-specific and program-wide, that means globally valid, variables. All variables used within a block can be created quickly and comfortably in the variable declaration table. They are referred to as block local variables, such as the input and output parameters or the local data used in the block. These variables consist of the name, the data type, and an optional comment, and also, where applicable, an initial value that is used when the block executes for the first time. Project-wide used variables are created in the symbol table. The symbol editor can be started directly from the program editor. The symbol table includes, for instance, digital and analog inputs and outputs, global data such as memory bits and data blocks, as well as timer. The structure of the global symbol table can be compared to the table for the local variables. Moreover, detailed equipment IDs can be entered in it for quick identification of sensors and actuators. In the following section, we will demonstrate on a brief example programmed in ladder the language functions described above, and how they are supported by the powerful program editor. Our plant comprises two identically designed pumps that need to be controlled. For this purpose, we will develop a reusable function that can be used several times over in the program. All necessary signals are routed to block parameters, which will be assigned pump-specific variables when the block is called. We want to equip our program with the following functions: switching the pump motor on and off by means of a block, recording and display of the pump operating hours, symbolic addressing. We will now show you step by step how the blocks are developed and how the program is integrated into the CPU execution cycle. To do so, we have to enter the symbols, create the block, generate the user program, and load and test the block. In our case, a project has already been created in the CPU by means of the Simatic Manager. First of all, we enter the symbolic addresses of the global variables. To do so, we double-click the symbol table to open it. The symbol table contains, among other things, all inputs and outputs required to control the two pumps. After editing the symbols of the global variables, we need to create the new function in our project. In our case, this is function FC2, which will contain the user program of the pump. A properties window opens automatically. We enter in it a symbolic name for the new block and add a symbol comment. After the properties window has closed, the block is stored in the project's block container for further processing. The actual program development starts by opening the newly added block. This action starts the program editor. Since we want to create the pump block as a multiple call function, we first have to specify the block interface by means of the variable declaration table. In our case, the interface is composed of 5 input and 5 output parameters. The symbolic names assigned here to the block parameters will be used later for generating the program. They make the code easily readable and provide, as required in our case, the possibility of multiple calls. Now we start to actually develop the program within the block. You are assisted in this task by the program element catalog, from which all functions required for program development can be placed in the program development area by drag and drop. In our case, we have completed the first network in which part of the pump block logic is stored. The subroutine is easier to read if you assign a network title and a comment. In a second network of the pump block, the required operating counter function is created. We use for this the system function SFC 101, which is contained in the standard library that comes with the project. This function is now also available to the programmer in the program element catalog and can also be placed in the network by drag and drop. Next, we assign variables to the inputs and outputs of the function. Programming the pump block is now completed. We now save the block. For the pump block to be able to control both pumps later on, it must be called once for each pump in organization block OB1. We open OB1 and place the pump block in two networks by drag and drop. The block interface is assigned the variables of the first pump. Symbolic addressing can be used for this. We create the second network containing the control of the second pump in the same way as the first, using the inputs and outputs for the second pump. After saving the pump block and its associated organization block offline in the project, the last step is to load the newly generated program into the CPU's user memory. To do so, we highlight the blocks and call the operating function in the menu bar of the Simatic Manager. After loading the blocks into the CPU, we can go online with the same editor to have a look at the status of the pump block. We have shown you in this module that the three standard conforming programming languages, ladder, function block diagram, and statement list, due to their large inventory of commands, their easily learnable programming structure, and the Windows conforming, intuitively operable program editor, are powerful tools, both for newcomers and for experienced programmers, which allow you to save time and costs during the implementation phase.